All right, so as promised, I'm going to show you this demonstration that allows us to observe the formation of copper hydroxide precipitate and then the redissolving of it to produce the copper tetraammonium complex. So what I've got here for my demo, I have a bottle of 0.05 molar copper sulfate solution, and you can see it's a pale blue color. I'm going to put about 100 milliliters of this solution into an Erlenmeyer flask. So we can see, as expected, it has a pale blue color as, I guess I'm wearing a blue shirt. It has a pale blue color. That's the standard copper 2+ water complex. So water also binds as a Lewis base to copper to give it the blue color as an aqueous solution. Set my copper aside. Now I've got a dropper bottle of 50% ammonia. So it's 50% ammonia as we purchase it as concentrated ammonia. That makes it about between 7 and 8 molar ammonia. So I'm going to carefully add a few drops. I want everybody to observe the color changes or cloudiness changes that occur because of the additions. So I just a couple drops, and we can see that it turned cloudy. The color didn't change much, but it's distinctly cloudy. It's no longer an aqueous solution that has precipitate. Any cloudiness is a precipitate. So I add a few more drops and swirl. Not much color change yet, still getting cloudier and cloudier. Once it gets cloudy enough, you really can't see more cloudiness, but you might notice that right where the drops go in, there's a bit of dark blue color. It might be hard to see on the camera. As I swirl it, that goes away. Let me turn the white spot away from the camera there. So I'm going to add a few more drops. Still pale blue and cloudy. Add a bit more. Still pale blue and cloudy. A few more drops. Still pale blue and awful cloudy. A little squirt in there. Now we're starting to see a color change. It's getting darker blue. There's still cloudiness. Add some more. It's getting darker blue. Darker blue, darker blue as we keep adding more. That darker blue color is the copper ammonia complex. So what's happening here is the copper initially precipitated as copper hydroxide. That precipitate stayed even though I kept adding more and more ammonia. The precipitate stayed because its KSP was so small. That KSP, as we've done a lot of calculating, allows us to calculate how much copper is still in solution, right? So if the KSP for copper 2 hydroxide is 4.8 times 10 to the minus 20th, you can expect there to be a very small amount of copper that remains in solution. The more ammonia we add, we get to the point where there's enough ammonia to start forming the complex. The ammonia starts stealing the copper ions away from the other equilibrium and converting them into copper ammonia complex. That depletes the copper concentration in solution. We call that free copper. The free copper, just Cu2+, concentration starts to drop. So Le Chatelier's principle in our first set of equilibrium says if this goes down, shift to produce more of it. So more of the copper hydroxide dissolves. The more ammonia we add, the more we steal. The more we steal, the more of this dissolves until we convert it all into the copper ammonia complex. And that's what we have right here. Now, you can kind of see that it is transparent. There's no longer any precipitate. I'm just going to dump a little bit of it out and add some water. So that I can show you that it is transparent. I just dumped about 3/4 of the mixture out, and I'm going to add some distilled water. So I'm not changing the relative concentrations of copper or ammonia. So the complex still stays, but you can see that it is transparent. You can see things moving behind the flask, hopefully on the camera. So all of the copper hydroxide has redissolved. And the key to the whole thing is that when you form the precipitate initially, and then you start adding more and more of the precipitating agent. Up here we added ammonium hydroxide as a precipitating agent, and the copper 2 hydroxide precipitated first. we add more and more and more to it, we get the concentration of ammonia high enough, it starts to steal the free copper ions out of the solution and form copper ammonia complex. So this equilibrium starts feeding into the next equation. This one feeds this one. As we deplete the copper, more dissolves. And as we keep going, keep adding ammonia, eventually we redissolve all of this copper hydroxide and make the copper ammonia complex. So this second equilibrium step has a K value. They call it a KF for formation. The formation constant for the complex ion, they're usually very large. If they weren't very large, we wouldn't observe the complex. Okay, so these values, and there's some in your book, there's a table in your book on page, let's see, 844. If you don't have a textbook, do a Google search of formation constants for complex ions, and you'll come across a table of all sorts of ammonia complexes and cyanide complex, water complexes, even chlorides and iodides and bromides. They're all out there. But KF for this is very large. When we come back on our next video, we're going to talk about how to determine what the free copper concentration is in one of these situations. It's not as bad as it looks. We don't need both sets of equilibrium. We're only going to work it on the second step there. Okay? So we'll come back, we'll work an example.